Okay, I'm going to be talking about work I've been doing with the folks in Huntsville to characterize lightning location system data and to try and help them work to relate the low frequency data to the expected GLM data set that we'll be having in our hands fairly soon. I'll be covering well, some background is good. GLM needs all kinds of lightning system data because they all come in different spatial locations. I mean, if all the data was perfect, we wouldn't be needing to have GLM. We need GLM, but we need to find ways to both create the proxy products, as I mentioned earlier, but also adapt those tools and that knowledge that we have from the proxy products and put it in place for validation post-launch. There'll be a one-year period or so for sure. Well, there'll just be a mass of analyses being done on the first-year GLM data to make sure that the quality is there and the performance is there and people gain confidence in it. So proxy product generation, as I talked about before, post-launch validation. We need the cloud-to-ground data sets. We need the long-range data sets, data sets. To use them, we need to quantify them. We need to know how to upscale them. Like Hartman was talking about, you take a data set, you understand its limitations, and then you upscale them a little bit. You feed in what you need. And you can't always make a 7-station, 30-kilometer baseline network. Even if you put it out in buoys in the ocean, you would need hundreds of them. So we will be upscaling data. To do that, we need to know the quality quantitatively, how to convert it to an approximation. And then I'm also involved in trying to better understand the relationship between the VHF and low-frequency ground-based data sets and Ligh, like a lot of other people are, so that we can do this more intelligently. So first I'll be talking about some space-time exploration tools that I've worked on, and then a description of an LLS intercomparison tool. Not a lot of results, a few little observations along the way. Hasn't been time to do a lot of results, but there's a lot of data to do. So when we have another workshop in a couple of years, I'll be able to show some data. This slide is meant to, I hope that means just go ahead. Qué lástima. Oh, bueno. This was supposed to be linked. I said, maybe I'm okay. It's supposed to pop up. Maybe it's going to take a while to pop up. Maybe today is not tomorrow. Ah. Team? What? Oh, did I do an update? I did. No, don't say no, cancel a yes. All right, so the purpose of this, can I pause it? This is a different interface than I'm used to. Stop. Doesn't stop. So you see, do you see? Can you see the Ligh field of view traveling across the map? Yes. Shoo! Okay. So the purpose of all this is, can I stop this? This is not my interface. I have control. So what you see here, to begin with, I don't see a stop button. That stop? Not a very friendly interface. All right, I'm sorry, I'm wasting time. These are all of the Ligh sources. As they come into the field of view, they will brighten up and flash. You also see woolen data as X's and LMA data as colored dots. And the important point to be made here is that you can't just grab a domain and count. and think that you're comparing anything, because they have to be spatially and temporally related, and you have to limit your data set to that, or you'll make a mess of the analysis, which I did for a while before I fully understood it. And by using tools like this, you get a flavor for the dynamics of the interactions between the data sets and the spatial extent of the data sets. Woolen covers large areas, LMA moderate-sized areas, Liz cuts a swath as a function of time. Complicated limiting that you have to do to understand and use these analyses. Now, am I going to be able to get out of this, folks? How? Escape? Fire. Okay, got through that. So, I'm sorry I spent 5 minutes on that. So the first work is to do the spatial and temporal analysis with Liz. The panel on the left is not seeable, and I don't expect you to see it, but I want to tell you about what it is. The data, all the data presented in the plots are limited by the Liz swath coverage on a per second basis. If you take the whole swath, you'll mess up the analysis. Liz groups have a center and a radius defined by their area, and they are magenta circles. The LMA sources are color-coded by time, and then the cloud-to-ground data is red dots in the spatial plot here. And then for exactly the same overpass conditions, I produce a temporal plot here. This is time. This axis is height of the LMA sources, but it's also the distance of the centroid of the Liz group from the 7 nearest in space and time LMA sources. So we can synthesize the data and make room for all of the simultaneous. This particular quality of image, these don't necessarily look like dotted circles, but they're dotted circles and they're the Liz groups. You see the LMA data, time scaled here, and you see the cloud to ground data plotted with it. This is Sao Paulo, this is San Jose dos Campos. And out here, you actually have just a few Liz groups associated with that LMA flash. So I'm showing you the tool more than getting into details. This is a zoom in on just a few seconds of data. Again, the Liz groups, their size in this case is radians. This is a large cloud-to-ground discharge. You have fairly good radiance, a modest number of LMA sources with height. The centroid of the Liz groups are a fair distance away from the LMA sources. Some of that could be the parallax that has been discussed in earlier discussions. Some of it is the fact I'm taking the centroid and not the edge. There's more work to be done there. But I'm trying to produce a tool where I can explore it and gain physical insight before jumping to broad-scale statistics. So here's a flash not seen by not having any ground pulses. This particular one did, this one didn't. This has a lot of fairly large amplitude, high radiance, Liz events, no cloud-to-ground discharges. I'll step over to this one here, and we have this huge factor of 10 higher radiance associated with this one particular flash over here, and I will zoom in on that a little bit more. So I can take the tool and zoom in space and time. Here is earlier time to later time. So this flash originated out here at what would be the edge of this rather high radiance, or at least a large area discharge, and propagated maybe 8 or 9 kilometers to the northwest. Then there's some cloud-to-ground discharges there, and then later in time, there's some more LMA sources and cloud-to-ground discharges. This is the time series for that discharge and time height. So what you have is a horizontal propagating leader from the lower portion of the cloud, from the negative charge region, traveling for a few tens of milliseconds or so, and then a downward leader to a ground stroke. And at the time of the ground stroke is when that particularly high radiance discharge occurred. It's pretty clear between this image and this image that this is a discharge that is moving essentially out away from a core. You normally, if you have a normal cloud-to-ground discharge, the leader propagation is mostly vertical. When you have this kind of propagation, you're probably moving towards the edge of the cell. I need to couple radar data with this, but I hypothesize that this event actually came out towards clear air. And you have a modest peak current. I think this is under 30 kiloamps producing that radiance because you've got no cloud volume above you potentially, and possibly you're also reflecting off of other cloud edges, so everything enhances what gets seen from space. So the radiance will be a complicated function, not only of peak current, but other things. I'll now move on to the second half of the talk. Do I have about 5 minutes left? Huh? Okay. I've also developed an intercomparison tool for ground-based data sets that I can also apply to Ligh groups. It was designed for the NASA folks so that they could take any data sets, specify the coding of the ASCII files from the different networks in a configuration file, and then just run the analysis. And there are various sheets of analysis. The first one plots the time correlation of the data and the position differences between the data sets when you compare time correlated events. So in this case, we correlated the TLS cloud-to-ground data and the GLD 360 data in the Chuva domain. They're time correlated with a timing standard deviation of 16 microseconds, and this is the position difference histogram, and most of the position errors are defined by the GLD 360. We count the number of events during this particular day. The LF network saw 137,000 cloud-to-ground strokes, and the GLD 360 saw 109. But they only correlated about 50% with each other, so they're seeing some slightly different members of the discharge. You can also, with the tool, and I can provide, since this tool was developed for NASA, if people are interested in it, to use it and things like that, the tool can be provided, and I have a document that describes what it does in a lot more detail. But this is a sheet that you can do if you have peak current information, and I'm going to focus on these bottom two slides. We can make a two-dimensional histogram of scattergram of peak current between the two networks, and the slope of the line tells you how well their currents match. The scatter tells you the random errors in it, and if you see diagonal lines like this, they represent the events that had polarity mismatches. In this case, 98% of the data had the same polarity between the TLS cloud-to-ground and GLD 360. And you can also plot detection efficiency as a function of peak current using the tool for positives and negatives to really gain an understanding of the intimate relationship between the network data sets. And you can plot quality data that I'm going to leave to the interested person to read me about it. I've also correlated the data sets Ligh groups with GLD 360 and the TLS network data at the flash level. And I'm going to give a flash summary as a kind of a final results slide. I produced flashes from the Ligh groups. I took events that were within 30 kilometers in a half a second because of the spatial uncertainty of the Ligh centroids and the GLD 360 data. I determined mean group and flash rates. I identified the time-correlated flashes. And this is a table of results where we determine the relative detection efficiency of the TLS cloud-to-ground data of the Ligh flashes, producing one or more events. And that's consistent with, I think, Amitabh's finding. I found mean values of 7 to 8 Ligh groups per flash in the data set that I analyzed. And the number of strokes per flash in the LF networks varied from 1.94 for the GLD to 2.78 for all the sources. So these are tools that are available to Chuva participants, and NASA people will be using it. I'll be doing analysis for NASA with these tools. And basically, the summary is that you need to be very careful about how you correlate the LIS data for all the reasons that I spoke of. There are the LIS FIFO overruns that that Jeff Bailey talked about. They're there in a lot of the data sets, and you need to exclude that if you want to quantify relationships. The radiance is a complicated function of peak current, channel geometry, and path, no doubt. Be looking at that kind of data for quite a while. I've summarized the performance recently already, so I won't dwell on this slide. Future directions will be to analyze and compare all the TRUVA data sets, speaking with the other collaborators that are contributing data, and compare them all to LIS groups and flashes. Try to use these results to statistically upscale to produce proxy data, and then formalize the correlations between LIS and the physical properties of LIS, flash area, and group and radiance. Thank you.